Welcome to Blue Pen Land. All right, so we've got this circuit here. This is actually fairly accessible, and this gives us the impression that maybe we have a chance on the IV test, right? Notice that these all have a resistance of 4 ohms, so I like to label that 4 ohms, right? And the switch is open. Calculate the total power dissipated in the circuit. I think you can do that. I don't think you need help. I think the best way to do it is V squared over R would be what I would do. But there's all sorts of ways, and you really should be able to do this, okay? And then it says the switch is closed, state without any calculation, right? Well, yeah, go ahead and calculate, right? Huh? Well, they know. Okay, why the current in the cell will increase, right? Remember in a parallel circuit, right, every time you add a parallel branch, current's going to flow on that branch, right? And it doesn't have anything to do with this resistance being less than these resistances. It's just that current is, when you close that switch, it's going to, before the switch is closed, it only goes this way, right? After it's closed, it goes this way, and it goes this way, right? So hopefully you looked at the circuit FET and you understand that just giving it another path for current will cause more current to flow, right? And that's the current in the cell. Closing the switch, by the way, doesn't change the current out here. This current goes from 0 to something, right? Okay, and then it says deduce the power dissipated with Y and Y, right? With the switch open and the power dissipated in Y with the switch closed, okay? And this is kind of funny because they got me. This is like a total trick question, right? This is like, Simon Says or something, right? So you figure out that the current will increase, right? So you're thinking that it has to do with the increase of the current. But they're talking about Y. They're talking about this guy right here, right? And this thing is a parallel circuit. So when you open this, it doesn't change the current in this at all, right? Current stays the same. Voltage across this stays the same. I think you can get it, right? I definitely missed it, right? What I did was I calculated the power dissipated from the cell, which isn't it, right? I mean, I thought that was, good question, right? And then, I got it wrong. So, sorry about that. And it gets more difficult, right? Okay, the cell is used to charge a parallel plate capacitor in a vacuum, right? With no dielectric, evidently. The fully charged capacitor is then connected to an ideal voltmeter, right? So it's the cell, by the way, if you were paying attention, is a 12-volt cell, right? So this guy is charged to 12 volts, right? The capacitance in the capacitor is 6 microfarads, and the reading of the voltmeter is 12 volts, right? Energy stored in the capacitor, you either remember that it's 1/2 CV squared, which, by the way, this is very similar to 1/2 kx squared that we used last year, right? It's a very similar thing, right? As you put charge on that capacitor, it gets harder and harder to put charge on it, right? Let's see. When fully charged, the space between the plates of the capacitor is filled with a dielectric with double the permittivity of a vacuum. Now, here's the thing, right, is that now it is disconnected from the voltage source. We must understand that, right? It remains disconnected, right? Okay, and it's got double the permittivity. So basically we're going to double the capacitance, right? Okay. Okay, do we understand that? Because what is it? The formula for C is that it's epsilon naught area over D, right? So if you double this, right, if it's twice the permittivity, right, it's just 2. It's just twice that, right? So what are you going to do here? The first argument here is you're going to say, well, the capacitance doubles, right? Okay. Well, if you double the capacitance, the voltage on that is Q over C, right? Because C is sort of like the space into which the charge fits, right? Okay. So if you double the capacitance, you will cut the voltage in half, and then you're going to use 1/2 CV squared again, and you're going to use it with twice the capacitance but half the voltage, right? And you'll see that there's a relationship there, okay? It actually has less energy on there, okay? So, but remember they're saying calculate the change, so you're going to have to subtract. You'll know this answer, and you'll have to subtract it. So again, you're going to double the capacitance, which will cut the voltage in half, and then use this formula again, okay? Suggest in terms of conservation of energy the cause for the above change, right? Well, it lost energy is what you'll find out, right? So how could it lose energy? And I'm not even sure IB knows the answer to this. okay, because it said that the energy goes, that the answer in the Marx team makes no sense at all to me. I would actually object to it formally if I was one of the graders. I believe it says the energy lost goes to work done inserting the dielectric. Okay, and this is just all wrong, I feel. Okay, so this is an intriguing thing. Let's imagine that we've got this capacitor, right? Okay, and if we stick a dielectric in there, right? Let's imagine that we're sticking a dielectric in there, right? Which is just going to be like a chunk of plastic, typically, right? As I stick that in there, let's say this is the positive side, right? Remember that we're going to get an induced charge. This is an organic compound or some kind of insulator, right, where we can induce a charge. Those are the good dielectrics, right? So that means the top of this is going to have this induced charge that's negative, and that's going to be positive, right? Right? So what happens here is that this, sorry, I'm just getting all geeky about this because this is kind of a funny question, right? As you insert that dielectric, right, as you put it here, it actually gets sucked into the capacitor, right? So it's not that we do work. See, if we did work pushing that dielectric in there, the voltage would increase on the capacitor, but it doesn't. It decreases, right? Okay, so we're not doing work. It actually does work on the dielectric, right? It would suck that dielectric in, right? Now, if this is a frictionless surface, of course, it would overshoot and come out this other side, and it would go back and forth and wing, 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 wing. And the reason it would do that is, of course, it's attracted, right? This negative would be attracted to that, and it would just suck that guy in there, right? Okay. Ultimately, though, even if this was a frictionless surface, this thing would become a RF generator. It'd sit there and oscillate back and forth. The oscillating charge would send off electromagnetic waves, which would eventually dampen it down, and you would end up with the result that you calculated here, that it lost a certain amount of energy. Okay, sorry for that tangent, but it's just fascinating. And I think they're wrong. I mean, you'll have to look at the thing, at their Marx scheme, and give me your opinion. I think that's the end of that one, isn't it? It doesn't. All these are like good for about 2 pages. All right, good enough.